How about this one? Sorry.
It's quite clear.
Is clear?
Yeah, it's clear.
Okay.
Both the video and the sound.
Okay, sounds good.
Awesome. Okay. So well, we'll wait for 1 or 2 more minutes for people to join. So uh, this is our BCI course in the Department of Computer Science at National Yangming Jiaotong University. But since we're going online, and so this talk is also open to a lot of friends that I invited, and also friends from Tsinghua University and other places in Taiwan, in the BCI and EEG community. And it's also shared. His information is also shared to the IEEE Taipei chapter, thanks to the help of Professor Ke Wei. So I can see some old friends here. Yuan Bing, can you hear us?
Yes, I'm here.
Good to see you. Yeah, and 冠志学长, hey.
Hello, hello.
Welcome to our class. Okay, so I guess it's time to start. So, hello everyone. It's my great honor to have my respected advisor, Dr. Tzyy Ping Jung, to give a talk in our BCI course. So I met TP in the summer of 2010 when I was a master student at Jiaotong University. About the time when I joined the Brain Research Center, led by Professor Lin Jingden. So at the time, I had a chance to meet TP and start working on EEG research with him. And later, I was lucky to have a chance to join his team at UCSD and starting working as a PhD student with him for more than 5 years. And so on the first day I joined the lab, TP told me an important thing that I still remember is that you need to have passion to support what you're doing. And I think now I kind of realize what this makes a difference. So we do a lot of things without motivation, but passion is much more than that. It can support you to do things for decades. So here we can see what TP has done in this field of research for decades, which is remarkably outstanding. And meanwhile, TP always keep the connection with Taiwan, helping anyone and share his research with people in Taiwan. Every year, almost every year he came back to Taiwan and talk with others and do a lot of talks and a lot of collaborations. And he's always open-minded to share everything he has in his research, and also do collaborations with 110% of the effort. So it's really my pleasure to introduce Dr. Tzyy Ping here, Dr. Tzyy Ping Jung here, and I hope we can all turn on our microphone so that he can hear the applause. Okay, please.
Thank you. Well, thank you all. First of all, I would like to thank Professor Wei for inviting me to give a presentation in his class. I just learned that there are people from National Tsinghua University attending this talk. Actually, I'm going to give another talk to Professor Michael Zhang's group next week. So it will be slightly different because I believe that group is more focusing on machine learning and BCI. So I will focus more on the machine learning part, deep learning. And if you are interested, and you can join us. I think Professor Zhang will be happy to have you. So this talk is sort of a more general talk, and I'm going to cover a lot of ground. The second talk I'm going to give next week will be more on the data analysis part of the BCI. Okay, you probably have heard of brain-computer interface in the past few weeks, so I don't need to give you sort of very basic introductions to the field. However, the BCIs you have learned were probably from very exciting BCI demonstrations in well-controlled laboratories. Today, I would like to discuss and focus some of the challenges that particularly this field faces in translating laboratory-based BCI demos to real-world applications. So that's why I put real-world BCI challenges and opportunities as the title of my presentation. Before I begin my presentation, I would like to make announcements about a scholarship available to all Taiwanese students. So this is a foundation at UCSD, and we receive a donation from Tzyy Young's family and foundation so that we can support new graduate students from Taiwan. This is not limited to Yangming Jiaotong University or Tsinghua University. And we will offer up to $25,000 in tuition and fees and salaries and to students who committed to study PhD programs at UCSD. However, this is not sufficient, I know. In fact, the department or your advisors have to get matching fund. So from the grants or from the fellowship for other sources. So because each student need to will cost about anywhere from 50,000 to 70,000 depends on the department. So, but that's not your job, and your advisors or departments who are trying to compensate. So this is for new incoming students, and we also offer support to the continuing students at UCSD. But the priority goes to the new incoming students. In fact, this year, as I recall, I'm a member of a steering committee, and I think we admitted 9 students from Taiwan. So they all get an offer of this scholarship. And I will encourage you to apply. Well, actually, you should mention this in your application that you're eligible to apply, because your department needs to nominate you for this scholarship. It's not an application from the students. And foundations also offer exchange faculty fellowship, so allow the professors to come to UCSD to collaborate with faculties at UCSD, and also offers support to have a joint workshop between any Taiwanese research group and UCSD. So that's the scholarship. Okay, so let's go back to my presentation. This is the outline of my talk. I will first explain what the brain-computer interface is, even though you already know that, but for the sake of completion, I will mention that. And then I will follow with the big crucial issues in BCI. In short, is BCIs in BCI. And then I will tell you the recent progress in resolving the BCIs in BCIs. Finally, I will show you some sample BCI studies, which we have tried our best effort to translate the laboratory demonstrations into real applications. So this is going to be a long talk. I will try to go as fast as I can in the first part, and then we will leave more time for questions. Okay, BCI. What is BCI? You already know BCI. BCI is a direct communication pathway between the brain and the external device. You probably have seen these pictures. This is probably one of the most cited figures in the field, done by Wolper's group in 2002. And as you can see in these figures, we have human brain. We measure the EEG signals or any other brain signals with the acquisition systems, and trying to do the feature extractions and then translate those signals into command controls so that we can interact with external device. Sorry, I go really fast because I know you already know that. Okay, what are the BCIs in BCI? If you want to translate this technology to real world environment, first of all, as you know, and the BCI field has made a lot of progress in the past, I would say 20, 30 years. However, if you look around, you see BCIs have not been in widespread and routine use. You probably cannot even name one which people are using at the time, currently. So all the stuff we see on YouTube, even in your class, are actually laboratory demonstrations. And why is that? And that's what we're going to go through today. The first, I think we don't have new sensors or technologies to measure high quality neural, physiological, behavioral, and contextual data in real environments. I will elaborate that later on. But neural, as you know, is we're talking about EEG, function MRI, whatever, the neural imaging modalities you can use to measure the signals from the brain. Physiological, for instance, I'm going to share with you why we need physiological signals. Something like eye tracking, galvanic skin responses, and behavior. No question about that. We need to know subject responses. But contextual data, for instance, what the physical or mental states of your subject. Most of experiments don't even care, or they never record that. Give you examples. If your subject actually had a really poor night of sleep, and if you don't know that, actually the sleep quality will impact your EEG activity, and most likely will impact the relationship between your EEG data or functional data to their behavior, to their cognition. Okay, so we have done at least 4 different longitudinal studies. We found that the subject's stress level, anxiety level, sleep quality will impact the models we built from day 1 to day 2. In other words, tell you the bad news, and one size does not fit at all. So the models you get, the pilot data from the subject cannot be applied to the second day. So that's a really bad news, but nobody actually touched upon. That's why we have a lot of problems, to translate the laboratory models to the real-world environment. Okay, and second of all, let's say you have all the high-end devices, you can collect data in real-world environment, but you still need to make sense of those data. To do that, we need advanced signal processing and machine learning algorithms to jointly analyze those multi-model data. That's the full data stream I'm just talking about, neural, physiological, behavior, and contextual data. Okay, and I think the most critical things in the field is what are the sensible real-world applications of BCIs? In other words, are we heading in the right direction? So for instance, you're trying to do the cursor control. Is that reasonable application in real-world environment? I have been working on SSVEP-based BCI and to help the locking patient to type. But locking patients maybe just a few hundred in the world. So is that reasonable, sensible real-world application? You have to ask those questions even before you're trying to create a BCI. So that's what we're going to go through today. This is probably the most commonly used neuroimaging modalities currently. On the left, EEG, you probably know that. Function MRI is the indirect measurement of your brain activities, and PET, same as PET. And MEG, magnetic encephalogram, is a counterpart of EEG, measure the changes in the magnetic field. So of course, it's much more expensive and bulky. And you can see that in all these modalities by EEG, the sensor is too heavy or too expensive. Even probably Bill Gates would not purchase a function MRI or PET machines at home to do the BCI because they cannot move or he cannot move. Okay, so EEG is the only modality that does not require the head and body to be fixed. But most of the people forget about this huge advantage of EEG. Okay, I think maybe you forget about this. That EEG allows head and body to move around, and you have natural gestures, hand movement, or body movement. But in most of the EEG studies, we ask subjects to fixate. We put them on the chin rest, which you will see pictures later on. So subject cannot move. So then what's the point of using this mobile neuroimaging modality? Why the experimenter do not let people to move? Because they're afraid of the contamination from body and head movement. So that's what we're going to go through later on. I already explained to you that EEG might be the only modalities allow us to monitor brain functions of unconstrained participants performing normal tasks in the workplace and home. However, as you know, that oftentimes we have a very bulky or messy connections and between the CAP and EEG device, and then we have computers behind that. So in the past few years, as you probably have heard, that we're trying to move this time-consuming and labor-intensive EEG recordings to dry electrodes. And as you probably already know, and you probably are using one of those dry EEG sensors and wireless EEG device. And this is my colleagues put up in Taiwan a few years ago. And this is Cognomics. I don't know if you have seen this. This is a polymer-based EEG sensor. When you push against your scalp, that will separate your hair. And this one coated with conductive paste, so that will get good connections between the skin, between your skin and electro and also EEG amplifier. So this is, I think, it's one of the latest quick 20 channels wireless EEG systems. Okay, so let's assume that you have very good EEG device in hand, but another things you want to do is to have to shift your mindset. As I mentioned, that this is a typical EEG setup. We have subjects wearing the cap and on the chin rest, and we get a lot of EEG signals, and you can time lock them to the stimulus onset, or for instance, onset of SSEP, visual stimuli. And most of the times, signal averaging, trying to increase the signal noise ratios. But you cannot do that in real environment. Because, for instance, you want to see the EEG signals when you watch signals turn green when you're driving. Okay, the signal is always there, so there's nothing pop out on the screen give you a stimulus lock activity, event marker. So, give you example. This is experiment done by Ximen Lin's group. Okay, published in PLOS ONE in 2017. Subject was asked to fixate at the center of the screen, and there's a series of photos will appear on the screen. They have to pay attention to a bike, okay, and they have to press buttons when they see the bike. If you do a lot, averaging across multiple trials, and in response to the pictures with a bike in it, you get ERPs, as opposed to if you time average of the non-targets, you get really flat or early on, evoke potentials. So then you can detect if subjects seeing the target versus non-target. But again, in real environment, there's no event onset. Okay. So how can you do that? And this is actually a little, sort of game I usually present in my talk. So this is a very, very popular picture book called Where's Waldo? Basically, you're trying to search the picture I'm going to show you in a minute and where the Waldo is. You can try. Yeah. So unfortunately, this is an online class, and I cannot see your hands. Once you actually find the Waldo, you can raise your hand. But anyway, I'm going to show you. I assume that you scan the picture. This is the Waldo. Okay. How can you find it? I'm pretty sure you actually scan through the pictures. And no matter your strategy is, you use your eye tracking. Well, you use your eye gaze. So in real world situations, we can actually measure your eye activity. We can try to find the fixation or trying to find the gaze onset to the target. So that's what we have been doing. In fact, we need more than just eye gaze and EEG. So I think we need more than that, because you can review what you can have. For instance, you can measure EEG activity, you can measure ECG, your heart, cardiac signals, your breathings, blood oxygenation level, or muscle activities. I have to sort of tell you, very ironically, until today, most of the times when we measure the behavior signals, it's very sparse and low dimensional. For instance, you ask that subject to press a button, or multiple buttons or keyboard, but still not the way we interact with your friends, your class, or in real world environments. So we need more than just a button press. We need more than just eye gaze. We need motion capture. So what we're trying to do is trying to collect all those multiple modality data. In these pictures we published in 2009, we're talking about motion capture, eye trackings, and dry EEG sensors. So we want to move away from this very simplistic, we call stimulus response contingency to a real world MOBI. This is called mobile brain body imaging. So to do that, we need software support. So for instance, we need stimulus presentation in real world environment, and we need lab streaming layer, which can record and synchronize all the data streams we just mentioned, like eye tracking, EEG, etc. We need to put into a format which can be easily interpreted. This is XDF. Recently, we have a more advanced data format called HED. And if we have time, we can go through that. But we also need advanced software package like EEG Lab. You have probably seen that EEG Lab, and currently we have 143 plugins to the EEG Lab. So EEG Lab is not a toolbox anymore; it's an ecosystem. I'm going to go through that later on. So this is the typical EEG setup. You're probably aware of, and this is the video I took personally. I took on March 16th, 2019 or 2020. But you know what happens later on. Now we have COVID. Okay, so we have few months we cannot actually perform any data collections because we have to practice social distancing. I think Taiwan is facing exactly the same problem. Okay, so in the past few years, well, this is actually last year, June 4th, we went back to the school. We can collect data, but in the past 2 years, I have been trying to work on a technology called Do It Yourself (BCI) or Do It Yourself (MOBI). In other words, we want to sort of identify the technology we can use. I should say, subject can use and to prepare themselves, as opposed to the technician, because we cannot have technicians to work with them. So, in the past few years, and my colleague, Professor Li Wei Ko, and his students, and our group trying to evaluate what kind of systems we can use in the DIY MOBI regime. So we actually evaluate the EEG systems on the market in terms of the channel count, the resolution, 24 bits or 32 bits or 16 bits. Battery life, that's important if you want to do long recording, and system cost. That's very important, particularly for your projects and your PIs, because they have to be able to afford it, and also the sampling rate. Okay, those are actually 16 systems we have evaluated. We put on this radar chart. You can see based on your applications, you can pick whatever you want. And we actually show several sample applications and to help you decide which ones you can use. I'm not going to go through this details. For the ECGs, nowadays, you can purchase very low cost and wireless ECG devices. Okay, for instance, I have been using Hearty Patch and also Viva Link and wearable, and you can measure that. This one, I think, even is waterproof. You can wear that up to 7 days, and I did that. I was one of the subjects. It works. And this is the eye tracking. And I think some of them can be self-prep. For instance, the desktop mount eye tracking systems. You can just follow a few steps and the subject can set up by themselves. This is, I don't know if you can see the movie. I hope you can. This is the computer vision-based motion capture. You can see this is totally open source. You can download from Google. This is called MediaPipe. Can you see the video. So this types of AI-based approach allows you to do the face trackings, in eye trackings, and motion captures, or object identification. So you can download those. Not only the new. This is just one of them. You can download open pose, dense pose, whatever, and that will help you to do the motion capture. So this is what I want to tell you. Nowadays, there are tools available and over the internet and can implement DIY MOBI if you want. In fact, MOBI has become very popular. Nowadays, there are 3 international conferences focusing on MOBI technology. And this is one our lab, our center is going to organize. If you're interested, please sign up. And this is a hybrid mode, so you can join from Taiwan. The conference will be held on June 7th to 10th this year in San Diego. I think there's a hands-on workshop 3 days before 7th. So if you want to learn all the technical details, you can join the workshop as well. Okay, this is a program. And yeah, June 5th to 7th will be hands-on workshop. Okay, and then talking about the hardware and software and applications in the conference. Okay, the second part of my talk will cover the advanced signal processing and machine learning algorithms to analyze those multimodal data. This is pictures we recently published in IEEE, I think IEEE transaction. This is preprint on arXiv. You can see again, we have EEG and data acquisition systems. And the first thing we will usually do is do pre-processing, or actually, I should say, we always do is pre-processing. Artifact removal, that's important for MOBI, particularly subjects' motions will introduce a lot of contaminations. Then oftentimes we do resamplings, we do re-referencing, we do filtering. And then we do feature extractions, and then machine learning algorithms, trying to do the classification or regressions. And oftentimes we actually split the data into training data set and testing data set. Okay. More recently, as you know, deep learning is very booming, and we're trying to use CNN again, and we're trying to use RN or LSTM, and we're also using transfer learning to leverage data from others to the test subject, because as you know, which I will focus on later on, is our EEG data sets. Usually, the data size is very small compared to the computer visions. You oftentimes have more than 1 million training samples, but that's not the case. Oftentimes, we have even less than 100 subjects. Okay, so how can we do that? We can leverage the advances in transfer learning. Today, I'm not going to cover all those, and I'm going to focus mainly on the pre-processing, because I believe that 100% of the people working on this area, they need pre-processing. Maybe 10% or 2% of them going to use transfer learning or RNN. So I'm going to cover the pre-processing step and going to mention the feature extraction, and hopefully we can go through a little bit in terms of machine learning classifiers. Okay, one of the sort of biggest challenges in the EEG data analysis is the signals we recorded from the scalp. This is a sort of cartoon, and you can see the sensors we place on the scalp. They are actually measuring all the activity taking place in your brain, not only the near field. They actually might project, higher amplitudes to the near the sensor nearby, compared to the far source. But more or less, they collect the data from all the parts of the brain. So there's not specific for the particular source. Okay. In 1994 or 95, my groups at the Salk Institute at the time actually developed the applications of independent component analysis or ICA, you probably already heard of, and to decompose the mixtures of signals collected from the scalp. In other words, EEG data. Particularly, we need multi-channels EEG data. The more, the better. Here, let's ignore all these equations. Let's look at the figures on the top right. X represent the mixtures of signals. Okay, A and X, are our sources. They are unknown, most likely. A is the mixing matrix, mix all these source activities to the scalp channels or to the function MRI data. Okay, neither the characteristics of the sources nor the mixing process was known to us. So we are trying to decompose the signals, which means X, and trying to find a copy of sources or components in this case, which will resemble the source activities. Then let's look at this very simple equations. This is our recording. We'll assume that we have a mixing matrix applied to the source activity to get our recording of observables. And U is independent components. And this is matrix multiplications applied to X. Hopefully, U is a version of S. And in fact, the U, the matrix we found, we cannot determine the amplitude of the sources or the order. So, but we can find the signals resemble the source activities. I'm going to share with you a video. I'm pretty sure that you have heard ICA many times in this class, and you probably have seen the demos on the internet. But the next one is the real life demonstrations. Okay, first you're going to hear recordings from microphones. This is actually done in real time. But I cannot play back the source activities while I listen to the mixtures. So you can see we can listen to one of the speakers. We can switch to another one, for instance, the driver, if you want to do the GPS. Okay, this technology actually has been commercialized and by a small company I co-founded called Softmax. In 2007, it was acquired by Qualcomm. So they put in the chipset right now pretty much in your cell phone. In fact, at least I would say 100,000 phones have implemented in this algorithm in the phone. Probably it's your phone as well. If you take out your phone, your phone actually has more than 3 microphones, not 1, 3 or maybe more. So they use the technology to separate different sources, then to pick the one which is closest to the headset as a main source. So that's why you can get denoising technology. Okay, go back to EEG. So this is a multi-channel EEG. You can see we color-coded. The one color represents positivity, no color represents negativity. At any given time point, you will see a scalp map. So this is nose, this is ears. And we assume there are linear mixtures of underlying sources. So each component, once we apply the W to the mixtures of data, we get independent components. So each component consists of two pieces of information. One is the time course of activation. The other one is projections of one source to the scalp. So this is the projection of this particular source. Okay, just like you just heard, this may be the driver, this is the passenger. Okay, then we're trying to identify which is which. For instance, right now there are several automatic plugins in EEG Lab can identify what are the, for instance, eye activities artifacts, why are the muscle activities, or blinks, etc. You probably have seen this. This is the main windows of EEG Lab, but what you didn't know is this package led by Arnaud Delon has been downloaded by 400,000 different groups over the past 17 years. This is an old message, 17 years, and has been cited by over 17,000 articles. And as I already mentioned, that this becomes an ecosystem. So many users actually contributed to this ecosystem with their own plugins. So including our labs. So this is done by ZenApp, and it's called neuroelectrical magnetics inverse source localization toolbox, trying to find where this signal is coming from on the cortical surface. Okay, and this is BCI lab plugin, and by Christian Cote. Another one is by Tim Moland. This is called Source Information Flow Toolbox. Basically, it's trying to find out interactions among different brain areas, as opposed to the amplitude of activities within each individual components. We're trying to find the association between the two. Okay. And you might know that we actually put up real-time data processing pipeline as well. That includes the pre-processing, data, and source localization, and granular causality measurement in frequency or time domain, and visualizations. Okay. As I mentioned, currently there are 143 plugins to the ecosystem. So you can download, so maybe you're trying to find something new, and all the tools you need to search the EEG Lab search engines, then you can find the plugins you need. So we cover the pre-processing part, and now we are trying to move on to other things. But I want to mention the challenges in EEG data classification, which is down here. And usually the number of label data are very limited and imbalanced across classes. Oftentimes, for instance, my group is working on EEG classifications on the subjects feels very stressful versus no stress. Okay, we have maybe 10% of data elevated stress as opposed to normal. So you can see this imbalance issues. And the other thing is human variabilities, both across different times, different days, within a subject and across subject. Okay, so that's actually, I would say, some major issues we have to deal with. The first sort of applications, I'm going to use these studies to introduce the data processing and classifications methods we use. This is emotions detections. So probably as long as humans have been self-aware, they are very interested in how we can identify the emotions. In fact, oftentimes when you talk to another person, you usually will observe their facial expression. For instance, they look puzzled. You probably will going to repeat your conversation. So emotion recognitions happens every single day. Oftentimes, they use subjective report or feedback to assess their emotion. Or, as I just mentioned, you can recognize their facial expression. But there are problems. Sometimes it's impossible to continuously receive users' feedback. Or if you want to use computer vision approach, the illuminations conditions might affect your precisions. And also it's impractical to have cameras everywhere. Well, probably in Taiwan it's a little bit possible because a lot of surveillance cameras. But that raises actually the privacy issues. Nobody wants to be watched 24/7. So that's why the biosensing technology might help. For instance, you can use a heart rate variability, you can use GSR, you can use EEG to assess subjects' emotions. Okay, what we do is we actually downloaded 4 different EEG data sets over the internet. Those are all publicly available, so you can download yourself as well. By the way, I want to mention actually emotion detections is way more complicated and difficult than just P300 BCI or SCP BCI or motor image BCI. Because even when you are watch the same movie or listen to the same music, different times you might have different emotions. In fact, we look at those data set and look at the subject responses. We found that this is really interesting. The same video, some people will score very negative mood versus positive mood, high arousal versus low arousal. So if you look at the 2D space, I'm going to show you the next slide. It's all over the places, even for exactly the same movie or same video. I mean, it's the same piece of music. Okay, in these 4 data sets, 2 of them actually use relatively high density 32 channel EEG. The other one is the other 2 only 14 channel EEG. So there is discrepancies among different data sets, and also the way how they actually collect ECG data. Here, and also GSR. So we need to deal with those discrepancies across different data sets. And this is one of the data sets you can see. This is called Amigo. And this is a video, sample videos. And you can see this is very funny, and at least for most of us, but not for others. We have received the scores all over the places, as I mentioned. This is a typical subject sort of setup. She's watching the video. I think so, total of 40 videos. I'm sorry, 16 for the Amigos. The Deep has 14. This data set is collected from 40 subjects. As I mentioned, each subject watch 16 short videos. And I want to mention that because you can see how small the data set is. You don't really have a lot of data to play with. A lot of people are trying to use, for instance, CN, RN. You have to keep in mind that you don't have a lot of data. And oftentimes, very sort of deep network or complicated networks, and will end up with overfitting. Okay, I'm going to go back this challenges over and over again, trying to alert you. You have to know what you're doing. Okay, this is data from the camera and also ECG, GSR. And for the subject responses, they have to report valence, basically their mood, positive versus negative, arousal, high arousal versus low arousal, liking or dislike, happiness, fear. So they all range from 1 to 9. You can see using this mannequin. Okay, this is emotions circumplex models. I'm not going to go through this very complicated because you cannot see the text anyway. So let's just focus on a simplified version. Y-axis arousal, x-axis valence. So different emotions actually you can place on this 2D space. Okay. Give you one example. Happy is positive mood or positive valence, high arousal. Okay. Bored or sleepy is negative mood and low arousal. This is Siddhas. He conducted a study. So this is easy data. I'm going to go through really quickly because you have probably analyzed easy data before. So we do the bandpass filter from 4 to 45 hertz, and then we calculate the power spectrum density in 3 different bands, theta, alpha, and beta bands. So we have 42 features for this data set. Again, different data sets have different number of channels. So if you have 32, you have 96 channel features. Then we use half-second overlapping windows across all the recording for each of the videos. Okay. And then we also calculate condition entropy, trying to find the correlations among different channels. Okay. And depending on number of channels, we have a different number of features. And for the 14 channels, we have 91 features in this case. And then what we're trying to do is trying to combine the anatomical, or I should say spatial information and temporal information. Most of the times, most of the study actually just consider the temporal information. For instance, they do stretch things into one dimension and fit it into any kinds of machine learning models. But in this case, we put it into the scalp, and this is the power spectrum in theta band, alpha band, beta band. Then we assign different colors, red, green, blue. So if you combine those, you get one scalp map, right? One scalp map. So this we consider as an image. As I already mentioned that we don't really have a lot of data. So the way we do is we actually use this combined image and fit it into pre-trained VGG16. That's a CNN model. So this is off the shelf. We did not retrain with our own data. We use pre-trained model. What we are interested in is the features this deep model or pre-trained deep model captured. And this is 4,096 features. Okay, and then we actually use PCA to down select to the 30 channels. And I'm not going to go, I'm going to go through this part really quickly. We can apply exactly the same way to get the pictures from the ECG data and the GSR data. So this is spectrogram. We'll use this as input for the pre-trained VGG network. Okay, and GSR as well. And for the facial expressions, we use 2 different approaches. We can use, first of all, we can pre-processing, we can resize into the standard size across different videos, different data sets. And we can also find the landmarks from each image, actually from each video frame. And we can calculate distance among all these features. Okay, in this case, we actually extract 30 features. Okay, basically there are 2 different approaches. We resize the figures, then we can use pre-trained VGG to pull out the features. We can also use this approach to come up with 30 features. So there are 2 different ways we analyze the face images of face videos. Okay, this is what I already mentioned. We feed it into pre-trained VGG network, we get 4,096 features. And those VGG actually pre-trained with 2.6 million features, images. Okay. Then if we have the features for each second, we can do long short-term memory, LSTM approach. Okay. We can also combine all these features within, for each video, for instance, 60 seconds, and we can use that as one data point to train machine learning algorithm, which is shown here. So this is extreme learning machine, ELM. You can definitely use other machine learning classifier, for instance, SVM. And the most important thing is most of the study already shown, that's the features you feed into the machine learning classifier. Okay, so this is a result from single modality. First, we want to see which modality, for instance, EEG compare against cardiac GSR, or phase 1, which is computer vision or VGG based approach. Phase 2 is a landmark based approach. And we highlight the one with highest accuracy. You can see it's for valence, for the deep data set, it's about 70 or 71 in EEG. And phase videos actually give us better results. But for across different data sets, actually different modalities will be preferable. Okay. And also, we also compare against the best results published before 2019. I didn't follow up, in the past 2 years. But also, we are interested if we combine multi-modality. For instance, we can combine all the biosignals. We can combine EEG with phase videos. And turn out, for deep data set, EEG and phase videos with LSTM give us the best result. But for Amigo, and that's different. Biosignals actually gave us better results. Okay, we're also trying to extract salient brain regions that pick up by the extracted by VGG16. So we're trying to understand the network we use. So we actually use a deconvolution network sort of back to back. And then we can see what are the important features. And for instance, you fit in different features. This one will mark which part of the image, and that's most important. In EEG, the data we collected, this is the top rows shows the different valence, and this is a different arousal state. You can see this midline frontal region shows the most differences, features, signals between high versus low arousal. I'm sorry, high versus low valence. And arousal is a little bit to the left, so it's lateralized, but it's still in the central areas. So that's why we know which part of signals will be most relevant and most important for the valence detection and arousal detection. Okay. In the past 2 years, I have reviewed many studies report incredible high accuracy. So I always wondered, how can that be? And then I realized there's a major concern. Well, first of all, they actually use EEG segments, for instance, 1 second segment, 1 second epochs within the maybe 60-second video. So they break down the EEG recording into 60 different segments. And they are actually were put into both the training data set and testing data set. So this is sort of very problematic because the EEG signals has very high temporal correlations. So you use adjacent EEG epochs. Sometimes they even use overlapping. For instance, they take an average of 5 epochs advanced by 1 epoch. In other words, different data sets might have up to 80% overlap in their data. So that's actually cheating. That's why I have seen maybe 95 or even 98% accuracy. Okay, as I already mentioned, overlap subwindows. And the number of data sets, training data, is very limited. So it's prone to have overfitting in this case. And most importantly, people studies emotion detection. They don't realize that the labels are often incorrect. Why is that? For instance, you're watching a 60-second movie, and this presumably is a sad movie or sad video. You're not going to have any emotion until maybe in the middle of the video. So how can you actually assign label subject report at the end of this video to each EEG epoch? They were wrong. For instance, you say, hey, this is sad, the first second. This should be maybe neutral. Okay. So if you come up with 95 accuracy in terms of second-to-second data point, and I will actually really think this is questionable results because the label are wrong. How can you get it right? Okay. And so the preferred setup is you have to use disjoint training and testing data set. The best will be leave one subject out. So you should actually use data from other subjects and to train your model and apply to the testing data set. Like Professor Yongping Lin, who is in the audience, and actually he used that. And at least you should leave one session out or leave one trial out. Professor Lin actually and I published a paper compared that. You can get at least maybe 10% drop in terms of accuracy if you do leave one subject out. But that's the fact. That's what we have to face. Okay. I talked about what are sensible real-world applications of BCI. I'm going to spend probably the next 15, 20 minutes to talk about that. First of all, I want to show you this SSVP, or steady state visually evoked potentials. I think you probably have heard of that, but for the sake of completion, I will just mention that briefly. SSVPs are signals. SSVP are signals that are natural responses to visual stimulations at specific frequencies. For instance, this thing is flash at 6 Hz. Within 140 milliseconds, your visual cortex will respond at exactly the same frequency. Okay, if I flash 9 Hz, you get 9 Hz. So that's we call SSVEP. Based on this technology, we have built one of the state-of-the-art BCI speller. I'm going to play the movie, but first one, let me explain. This is a virtual keyboard. Each block tagged with different frequency, which means they will flash at different frequencies. Like this is 8.2 Hertz, 8.4 Hertz, etc. They're also with different phases that we want to make it exclusive, so it's easier to decode. And subjects supposed to type with their brain activity by gazing different letters. For instance, she's going to type high-speed BCI 1 letter at a time. Okay, by looking at the blocks. Let's see. H, I, G, H, space, S, P, E, E, D, space, B, C, I. So the red highlight is just the feedback subject will receive. So she can confirm, oh, that was correct. It's not cue or guided SSVP. So you can see that we reach 75 letters per minute. That was the record in 2019. Okay. And a lot of people actually have been working on SSEP. So, but what is the real application? Yeah, right. You can use that on locking patients so they can type. But as I said, they might actually have other ways to type, maybe faster, without requiring wearing an easy cap. For instance, they can use eye gaze, they can use their hand, they can use their muscle. Okay. In other words, very limited number of even the locking patients will use this technology. So then what's the real world applications of this technology? That's the BCI. And a few years ago, I think it's 2016, Professor Yongping Lin at the time was a postdoc at the lab. And I and colleagues, for instance, Yijun Wang and Felipe Medeiros, who is a medical doctor, actually developed the applications in, sorry, I'm going to skip this, in using this technology to detect glaucoma, which is eye disease. One thought as a single disease, actually, now is a broad spectrum of group of certain patterns damage in the optic nerves. Okay, the worst thing is at least 50% of people with glaucoma do not know they are affected. Yeah, I know this is really well because my father-in-law has glaucoma. He didn't know until very late. Okay, so this is optic nerve of the normal eye or healthy eye. This is disease eye. You can see SAP results. This is our blind spot. So this is normal. Okay, we always have each eye has a blind spot. And this is disease eye. This is one has glaucoma. You can see a lower right quadrant subject cannot see well already. And eventually it affects the entire eye. This is not reversible. Okay, it's hard to detect because people don't realize that. And oftentimes they start with one eye and they usually the other eye will compensate. So you will not notice that until too late, unless you actually do annual checkup. Speaking of annual checkup, this is me doing the annual checkup. Okay, this is called standard automated perimetry. Okay, SAP. I stick my head into this, omidon, and then the flash. I think as I recall, green flash will appear one at a time in different regions of my retina or my visual field. I have to press a button when I detect those. Then I will have this sensitivity map. This is blind spot again. So the way we do that is we have this eccentric rings. Each sector actually will flash at different rate. So for instance, this is 9 hertz, this is 10.4 hertz, this is 10.6 hertz. If we flash in front of subject's eyes, well, actually we do one eye at a time. And then these signals go through LGM or reach your visual cortex. Then we can measure the ejectivity on the occipital region. We can look at the power spectrum. If the power spectrum of one frequency actually fluctuated a lot, not necessary to be low all the time, because subject is not blind. But sometimes they see that, sometimes they didn't. So it's going up and down all the time. And then we can look at which frequency it is and go back to the drawing board, know which part of region are affected. So this is our stimuli. You can see each sector actually flash at a different rate. And then we found that we can see which part of the visual field was affected. Okay, we can put this into the cell phone. It's on my cell phone, for instance. But the visual field will be too small to test the subject. So we put into a VR goggle or VR head-mount display. And this is Gear VR and cell phone based head-mount display. So you plug in subject, see the things cover the entire visual field, and we can measure the EEG activity on the back of your head, because over the occipital regions. And this is EEG amplifier and other supporting electronics. And then we can measure our EEG activity, particularly multifocal SSEP. I forgot to mention this is called multifocal SSEP. This is one sample result, and you can see this is diseased eye, this is healthy eye, and this eye, the top quadrants are affected. And you can see the SSEP results on the right. And this is healthy eye. There's no deficit in the visual field. So that's how we can actually measure, we can detect glaucoma. And this is a comparison between the current standard SAP versus multifocal SSEP BCI-based glaucoma detections. You can see the cost, the comparison, but the most important thing is in the US, the annual checkup, which means you can only check your visions once a year. Even if you have glaucoma, the doctor will check your eyes twice a year. But there's no information in between. And actually it fluctuates a lot because this is very subjective ways to assess your visual field. And this is objective way to do that. So you can do that as frequently as you want. So that's the very important part. Okay, then you can actually assess the progressions or the efficacies of your medication. That's why it's important to move the glaucoma detections from the clinics or from hospital to the maybe home use, or maybe you can go to the 7-Eleven, you can test your visions. Another applications we recently conducted is multiple sclerosis. It's an autoimmune disorder triggered by genetic or environmental factors. I'm not going to go through all these details, but multiple sclerosis actually affect your brain, spinal cord, and optic nerve. Oftentimes, we can detect that based on the visual test, the vision test, which has to test your afferent visual pathway. Means that if you refresh some stimuli, we're trying to find out if your brain responds. This is, again, visual cortex. So obviously you can think that SSEP is one of the possibility. But also we need to test the efferent pathway, which means if you can control your eye movement or saccade movement smoothly. So this is called efferent pathway. Okay. This is how we do that. First of all, let's go back to the glaucoma approach. And this is the visual pathway. And then we actually move this visual stimuli around on the screen. We ask subjects to track with their eye movement. So you have to follow the visual stimuli. That's how we can see your saccade movement and smoothing pursuit. So this is the current device we use. We use HTC Vive Pro Eyes because that has embedded eye tracking. And this is dry electrode sensors I just mentioned earlier on by our former student Mike Chi. And then we put this device on subject head, and we can measure their multifocal SSEP and their efferent dysfunctions. This is the comparison between a normal control subject and the patient. You can immediately see there's reductions in amplitude to MFSSEP compared to normal. So this is afferent pathway. And this is the efferent pathway. On the axis shows the positions of our visual stimuli on the screen. And Y shows the eye movement on the Y-axis. You can see ideally it should be on the diagonal line. So the normal subjects did pretty well. And on the right is our patients with multiple sclerosis. You can see they cannot control their eyes smoothly. It's all over the places. So that's how we can assess both the afferent and efferent pathway simultaneously. Okay, to sum up, I show you that one of the challenges we trying to translate the laboratory BCIs to real environment is we need sensor. We need sensor not only to acquire EEG data, but also the physiological data, behavior data from the unconstrained subject in real environment. We also need advanced signal processing and machine learning algorithms to analyze those data, to interpret those data. And I also show you a sample how the machine learning algorithms can analyze the data, not only from the EEG signals, but also multiple modality, such as the GSR, heart rate variability, and also facial images to decode our neural activity. We still need to explore sensible real applications of BCIs. To do that, whenever you're trying to develop BCI, you have to ask a few questions. For instance, is there any other alternative ways to do that, to allow our subject to communicate with the external devices? Is EEG the best approach? How that compare against other modality in terms of accuracy and ease of use? And also, ethical issues and etc. So there are many things you need to consider, trying to see if that's a sensible real application of BCIs. Okay, and I will end my talk with acknowledgements to my colleagues, and you can see Professor Yongping Lin is here, sitting over there, and this is Professor Chunshu Wei, and this is the old picture, as you can see. I also want to acknowledge the support from U.S. Army, NSF, NIH, and Schwartz Foundation. Okay, so I will take questions. Questions?
Thank you very much, TP, for a wonderful talk. So we're open for questions from the audience. So please feel free to turn on your microphone and speak. And also, you can type your questions in the chatting box. So, I have a questions. I have a question about the practice of BCI applications in clinical for clinical use, because there are regulations, clinical regulations we need to follow. So would it cause some challenge for us to deploy BCI applications for patients?
Yeah, definitely. And I would say that clinical applications is probably one of the most difficult sort of barrier to break into, because market to break into, because there is a really rigorous regulations, even if you're trying to conduct preclinical or clinical study, clinical trials, and you need to go through all these different IRBs and different regulations. So that's one of the obstacles we have to overcome. Give you an example for the, I recently published papers. We collect data from 4 different hospitals in Taiwan. And we have to get those data out of hospital. So of course, when you're trying to set up this study, you have to be able to access the data at the end of the study. Otherwise, we cannot, the data cannot leave the hospital. Then you're doomed. You don't know how to do. And the reason we actually collect data from 4 different hospitals, because oftentimes different equipments, different. Well, actually we use same equipment, but different technicians, different conditions, different environments, oftentimes will induce differences in the data itself. So that's why we actually collect data from 4 different hospitals. Okay, and we were able to actually get the data. Then we have to analyze data. Fortunately, we have one of the largest data sets in I would say major depressive disorders. We have data from 400 patients, or I should say 400 subjects, 200 patients with MDD, major depressive disorder, and 200 from healthy individuals. That goes back to my, the challenges I mentioned. We have to have enough data size. So this turned out to be one of the largest. I think this is probably the largest, data size in the studies focusing on MDD. Okay, and you mentioned, I'm actually answer the questions from the first part, that how can we actually get the data from the hospital and try to analyze. Then how we can to actually apply these technologies and use that on real patients. We have to go through FDA. So device has to go through FDA. If that's a medical device, you have to go through a 510K if you can find a predicate. Or you have to go through the full scale FDA approval or regulation. So that takes a lot of time, and sometimes years. Yeah. So you have to plan ahead. For instance, if you want to, at the end, you want to go through the FDA 510K, you have to document all the things you did in terms of how you design the device, how you, implement, how you realize the systems, how you test it one by one. You have to document it very carefully. Otherwise, you are going to pass the regulations. And of course, you have to present this. You can show the efficacy of your approach with proper design. For instance, you have to have control group, you have to show group, you have to have your experimental group carefully designed, and to show the efficacy to get through the regulations, to get the trust from the physicians, and then you can apply to your patients or subject. So this is a long process, but this is worthwhile because the things we develop from the lab, eventually we do want to just end up with just papers. We want to have as many people as possible who can use our technology. Okay, so I encourage you to do the clinical applications, but you have to plan ahead to design the experiment very carefully. Otherwise, I have seen many medical device companies, they end up with sort of retrospectively redesign the things from scratch. For instance, they didn't actually acquire a computer. By the way, the computer cannot turn back time. Okay, you cannot say you change the things you have done in the past. You have to document it every single details. For instance, why this thing fell? We found that impedance does not match. Then how you actually solve that? You have to document each step very carefully. Okay. Yeah.
Wow. Okay, Yuanbing, please.
Thank you, Tiki, for sharing your research progress. I always enjoy your talk very much. Even I join your talk several times. I always get something new from you. Yeah, I have a question that you mentioned. Yeah, we need user-friendly sensors and sensing technology to get the multiple model data to understand our brain's activity, how our brain interact to the external or internal situations. And also we can use the transfer learning or deep learning to build out a very advanced machine learning model to model our brain activity of types of interest. But you know that our EEG baseline are highly affected by several modulators, something like the mental status or attentional resources or stress quality. So in your opinion or experience, how we can really build up a reliable BCI infrastructures that can make the BCI work adapted to different modulators. So this really help the BCI can translate to our daily usage. So what would be the next step to deal with this kind of daily fluctuations?
Okay, that's a very good question. Actually, I didn't have the time to go through that. Today's talk actually is just probably 2/3 of the paper, the talk I delivered to the AI Center of National Yangming Jiaotong University in Tainan campus. That talk actually covered the other challenges I mentioned. I was trying to put up the slide I mentioned. Sorry, it's slow. Okay. What you're talking about is the human variability, both across time, within a subject, and cross subject. I didn't get the time to cover this. In fact, Professor Chunshu Wei published papers in Neuroimage, particularly addressed this issue, because we found out that across different days, the models we built, I'm talking about PCI model, of course, actually cannot be applied to different days from within the same subject. Then we figure out, and we need to find a way to mitigate the variability. First, across different subjects. Second, across different, different days, different times. So we use the transfer learning. Transfer learning in Chunshu's paper, excuse me, we transfer different models. So we train the model for each individual session. Then we pick the similar, or you can say supportive sessions from other subjects. And then you can group them. You can do majority vote. You can combine the model output. In another studies, we use tensor decomposition. We're trying to project the three-dimensional data into the low-dimensional subject space. So when we have a new subject comes in, we use their resting data, for instance, 1.5 minutes of data, just like Chunshu did. We try to pick the sessions and subjects which have the similar resting state EEG. Okay, so as you said, this is called baseline. So in real applications, this is how we do that. Let's say we have a big database. We have 100 subjects. Okay, then you can do the pairwise comparison between their resting EEG, and you can do also pairwise comparisons between the transferability, which means if I use the model from one subject to another subject, and also multiple sessions within subject, we can build huge matrix. Okay, one is for the resting data, one is for the performance data, the experiment data. Then when the new subject comes in, actually I should say even the new data from the existing data, existing or repeat subject, we use the first 2 minutes or 1.5 minutes data, and then compare against the big resting data set, and trying to pick what the subject we should use or what the session we should use. And then we can combine those models, or we can retrain our machine learning algorithms to build a new model for the new session. Okay, so this is sort of top-down level explanation. Then how can you get those data? You have to, when you do the design, experiment design, you have to prepare to collect data for multiple days for each individual. In our case, we measure their sleep quality based on the wristband. Tzyy is here. Tzyy, I think he participated in this study. So we collect data from the subjects, the same subject, when they have good sleep, 3 days of good sleep, when they have really bad sleep, 3 days of poor sleep, and also in the middle. So each subject we have 8 to 9 sessions from 8 to 9 days. And then we have the baseline. And then we can use the transfer learning. Of course, you can use multiple data sets, single data set from each individual and from multiple subjects. For instance, we do that for SSEP. And we show that even SSEP, which is probably the simplest responses to visual stimuli, and that varies across different subjects. Yeah, we can use the transfer learning to do that as well. We have published, I think, at least 7 or 8 papers using transfer learning on SSEPCI. To sum up, you need to design experiment to prepare your collecting data from multiple subjects under the same stimuli, which you usually do, but better you have to have a multiple session from each individual. And you should collect data, for instance, for resting state EEG and their performance, the sessions when they are doing the experiment. And you have to build up the models in terms of the resting EEG and also their experiment sessions, and are trying to see if you can transfer the models or transfer instance or transfer the features across different days, across different subjects to mitigate the human variability. Okay, did I answer your question?
Yeah, thank you. So that means for the daily usage, we still need calibration data from the new subjects or before the daily use, right?
Yes.
So
that's right.
text-free like resting data is much suitable for the daily use.
It's much possible.
Yeah.
Or you can use a related test. For instance, we have been doing this longitudinal study during driving, and you can use a very simple compensatory tracking, visual tracking test for a couple of minutes, and that's a related test, but you don't really need the entire hour. And hopefully you can see the EEG activity when they are under the high performance. You might not be able to see the low performance of drowsy data, but at least you have performance data. You can use that as opposed to resting data as well.
By the way, do you see any difference that how long of the resting data you need to make the transfer learning work?
Well, at least from our experience, we found out less than 2 minutes should be sufficient.
I see.
Okay, and also for the recent clinical applications, as I mentioned, MDD, we actually only use 3 to 5 minutes of resting EEG. We can achieve 84% accuracy on the totally disjoint or independent test data set.
I see.
Yeah.
Thank you. Thank you.
Okay, we have a question from You Chen. You Chen, could you speak your question?
Okay. Hi, Professor Zhong.
Yes.
I'm interested in the BCI field. So is UCSD a recommended grad school, and is it difficult to apply to?
That's a good question. Our lab actually is not degree granting department. We are totally research oriented. I didn't have a chance to introduce our lab. Our lab is relatively big, and we have about 7,700 square foot usage space, usable space. So we have, I would say, about 36 different offices. But our students actually come from the different departments: computer science, EE, cognitive science, bioengineering, everywhere. Okay. Where we have a living lab, which means they spend most of the time in our lab, unless they are going to classes. Okay. So our office is right next to our lab. To answer your questions, it varies across different departments. So in the US, department is sort of autonomous, compared to Taiwan. And also each professor actually is sort of autonomous. You don't really have a boss. So then there's so-called direct admission, and professor actually can take on the students if they have funding to support. And then, but the students still need to pass the sort of the standard. For instance, I don't know what the standard nowadays, GPA and TOEFL exams now to prove your English skill. As I mentioned, different departments, different, have a different criteria. So bioengineering, for instance, I'm affiliated with the bioengineering department. That's actually, that's, as you probably know, is a top 2 department in terms of bioengineering in the whole world. We're competing against Johns Hopkins University. So it's really tough, I would say. Oftentimes we get a few hundred applications. We admit fewer than, probably 100, fewer than 50 of them are actually PhD students. That's tough. Computer science, if you're trying to study data science, and I highly recommend you to consider that only if you have several publications. Because too many people want to do data science, want to do the data, deep learning, all this stuff. So it's very competitive. Other specialty have different levels of difficulties. So computer science, I think the number of admitted students increased tremendously in the past few years because we just could not produce enough students for the high-tech companies like Google, Microsoft. For instance, I have 2 PhD students graduated, got recruited by Microsoft. They're working at Microsoft. And I have 2 students that are doing the intern at Microsoft. Another ones will be going in the summer. So as you can see, it's high demands. They really need people. It's kind of interesting. Nowadays, industries actually recruiting a lot of people working on BCIs, probably more than you imagine, as opposed to academics, I don't see increase in terms of funding sources in BCI, but industries they put a lot of investment in BCIs. You have heard, Tesla's owner, Elon Musk, they invest, I think, $100 million to do BCI. So Coxside usually is very competitive as well, because cognitive science, this is a very top department in the whole world as well, because UCSD built the first cognitive science programs in the whole country. Okay. But BCI is sort of, I would say, small group in the Coxside. Most of them still focusing on basic cognitive science research. And Coxside, usually students do TA. So there are only few people got a research fellowship or research, we call it RA-ship, as opposed to TA-ships. Oh, I should go back to the computer science. What's your major? Computer science or OEC?
Both.
Okay.
I mean, yeah.
Computer science, there are many master students, because as I mentioned, the industry needs more people. Yes, we just cannot generate more enough people for that. So it's very hot, and oftentimes they have a very big class, particularly the first 2 years. So they require many TAs. I couldn't remember the standard. Usually, for instance, my colleagues teach a class with 300 students. So he probably needs at least 6 or even 10 TAs to help him out. So there's a lot of TA-ships. Yeah. I-ship.
Oh, okay.
Also possible. ECE has fewer openings for TA-ships. Oh, by the way, this will definitely affect how many people they are going to admit. So that will affect the competition. Yeah. I guess
Okay, thanks for your answer.
ICE or computer science. If you are applied computer science, particularly if you are interested in BCI, don't say that you are trying to do data science, unless you have many papers already. Otherwise, it's going to be tough.
Okay, thank you.
Yeah. If you are really interested, contact me separately.
Okay. Thank you, Professor John.
Yeah, I would definitely recommend students to contact TP Jung if you're interested in doing research at UCSD. I actually see a lot of talents in my class that has obviously higher potential than I did when I was a student here. So I really want to see if these great students can devote themselves into BCI research or to any kind of things they want to do. So TP is a good resource for us to get to know about the BCI research there. And is there other questions?
Oh, by the way, I forgot to mention, I didn't announce the International Summer Research Program. This is also offered by UCSD, and you can apply. This year, I think we admit 7 of them. You can approach any participating faculty members. But kind of interesting, this year I have 2 students want to work with me. One is from National Yangming Jiao Tong University. The other one is National Tsinghua University. And of course, both of them are interested in BCI, so that's why they select me. But if you want to explore, the UCSD to see if that's the right place for you, you should apply for this International Summer Research Program, or ISRP. You type in the Google ISRP and UCSD, you will find it.
Mhm.
I'm actually very surprised. Only one student from National Yangming Jiaotong University actually applied.
So yeah, so you guys are here, and as Tzyy Young Foundation is a very good provides a very good support, and also our university have some support for students to um, do short-term research abroad.
Mhm.
And it's actually a good timing since the pandemic has getting, I mean, I mean even how to say, so the border is getting more
Mhm.
open, so it's time to start traveling, I guess.
Mhm.
So it's a good timing to see if you can go to the US and do some research.
Yeah.
And is it for all level of the students from undergrad to grad student?
ISRP actually is for undergraduate students.
Hmm.
Okay, because the idea behind that is trying to recruit, trying to attract talented students
Hmm.
all over the world. Well, actually, this particular one is for Taiwan, so you have to be a student from Taiwan to apply for the ISRP.
Okay, so I think there's a good resource for any kind of purpose to visit UCSD if you're
Yeah,
Taiwanese through
yeah,
the Tzyy Young Foundation.
yeah.
Okay.
And for instance, Professor Lin actually was on what's it called Qianlima
Yeah.
program, and I have hosted the students from Taiwan in the past more than 15, 20 years. Our lab is very open-minded, and we're very international. We have probably covered 15 different countries in our 50 people.
Yes, if I recall correctly, I was the first Chinese Ma in your group
Yeah.
from Taiwan.
Yeah.
I have a follow-up questions that there are a few BCI group, even though it's quite small compared to other research community. So there is very limited in Taiwan that we can see the BCI industry. So what we are missing to create a BCI industry in Taiwan, because without the industry, we cannot motivate more students to join the BCI research. So what we can work for to facilitate the BCI industry in Taiwan.
Yeah, you're right. Actually, as I said, the industries in the U.S. right now is recruiting a lot of people, students who work on BCI, but not Taiwan. However, I arrived in Taiwan on April's 3rd, and in the past month or so, I have been talking to ITRI, ITRI, and also a couple of EEG or BCI companies. I see that there are more and more companies get into BCI, to your surprise. And maybe some of them are still sort of under the radar because they are still exploring different applications. They are trying to build their device. They're trying to develop algorithms. But I have talked to at least 3 or 4 companies. I can see more opportunities will surface in the next few years, and that's pretty much about the time and your students will graduate. Will graduate.
Thank you.
Yeah.
And I would say doing BCI research is actually a very good training for all kinds of
Yeah. BCI itself, is multidisciplinary research. As you can see, that you need to understand, the device itself, which means at least you have some background in terms of, EE, computer engineering or industrial engineering, and you have to know the neurophysiology and cognitive science, and you have to know the machine learning, which is hard area, and you have to put them together. You have to design experiments. So that's really good training program of his own. In fact, that reminds me, I'm trying to mentally count how many students, our former students actually in the industries now. I would say it's at least 10 or 15. So some of them are in very big companies like Meta used to call Facebook, and Microsoft, of course, is big ones, Google, etc. So I have one student and just finished her intern at the Meta. So you can see that, and they are actually recruiting globally. I think I saw some of the flyers that Google, Microsoft are actually recruiting people in Taiwan.
Yeah. Okay, so I guess this concludes our talk today. I'd like to invite everyone to turn on the camera so we can have a group photo. Okay, please turn on your camera. Okay. Let's wait for a couple of seconds. All right, turn on your camera. Okay. Okay, let me count 2, 3. 1, 2, 3, cheese. And another one. 1, 2, 3. Okay, thank you very much, TP, for a great talk.
Yeah.
And thank you for participation. Bye.
Bye.